Okay, Alex, so this is the first problem we're going to work on. This kind of set of notes is probably around 15-20 pages. I'm going through a lot more of the details in this first derivation, and in subsequent derivations it'll be a little bit easier, so I'll go faster. But you'll see kind of the basic idea of how we're going to transform the physical problem into a set of differential equations that we can work on. So, the problem is going to be diffusion into a sphere of cells, and that sphere of cells is going to be size r, or have a radius of r. It's going to be spherically symmetric, so whenever we start writing these out and we have the theta and phi terms, the radial components, they're all the same, so the derivatives are going to go to 0, and that makes it nice because it gets rid of a variable. Our boundary conditions are going to be that in the center of the sphere, the slope is 0. So dc by dr is equal to 0. So I'm saying c is concentration and r is distance from the center. And then the second boundary condition is that at the exterior, it's held at some constant concentration, which this is kind of our first problem. And as we go from this idealized problem to more complex problems, the boundary conditions are going to change. So this is the first problem we're going to solve. Well, you have to ignore the staining here. This actually got kind of a spill in a manila envelope, and the yellow from the envelope stained it. This is a pretty old derivation. You can see it from 2015. So we're going to start out with equation 1. That is Fick's first law, and then we know that the change in concentration with change in time goes as the gradient of the flux. That's the gradient of ions that are passing through into a little volume of space, plus this rho c, which is a mass generation or some mass subtraction. So this is kind of a generator term. So c is a function of both position and time, and it has units of moles per meter cubed. If we take equation 1 and put it into equation 2, we get this expression. So we get del D del C is equal to rho C. So del, to remind you, is a vector quantity. Well, it's the gradient term. If we're dealing in Cartesian coordinates, it would be dx, dy, dz. But we're not in Cartesian. But that's good, because by using this gradient instead of specifying a unit system, it allows us to have kind of a more generic way to work with the problem. So we're going to assume that we're within a limited volume and time period. The concentration does not vary sufficiently that d depends on position or time. So basically we're going to say that this gradient doesn't affect d, so d is just going to pass through it, right? Because this del affects c, this del affects the c, the d and the c. And this assumption that d is independent of position and time is, again, very much an approximation, because we know, strictly speaking, it does, but as kind of a first approximation, that's what we're going to do. So if the diffusion coefficient is independent of position and time, then that means that this expression becomes this expression. So now we get this del squared, and this del squared, this is called the Laplacian. L-A-P-L-A-C-I-A-N. Del squared. And the left hand and the right hand side of equation 4 have units of mole per meter cubed per second, because that's mole per meter cubed, and that's per second. So let's talk about this mass generation or mass subtraction. The mass generation term, one second here. The mass generation term we're going to use what's called Michaelis-Menten kinetics. And Michaelis-Menten kinetics say that the change in concentration is actually the change in concentration of product per time times some Vm, then the concentration of reagents divided by Km plus the concentration of reagents. Well, in our case, this concentration of the reagents, that is our concentration of what's diffusing in. It's oxygen or it is glucose. Vm is the maximum rate that it occurs at, and Km is the concentration where the maximum rate occurs. And if we write this out, it looks like this. So rho C is equal to Vm, C, our concentration, divided by Km plus C. And we have this negative sign here. That negative sign is because we have consumption, right? As the oxygen diffuses in, it's being devoured by the cells, and we want Vm to be positive, which means that we have to have a negative term out in front, which means that now our diffusion equation is derivative of C with respect to T, d Laplacian of C minus VMC over Km plus C. Okay? But again, we haven't put any coordinates in yet. So we're going to use coordinates that are spherical. So we're going to have a term which is a radius, theta, and phi. And because we have spherical symmetry, that means that the derivative with respect to theta and respect to phi are equal to 0, which is great because that means that the Laplacian, this Laplacian term is written out this way. And this is the Laplacian for spherical coordinates, and I think Wikipedia's got a site on this, so does MATLAB and Wolfram. So you can look for the derivation of that. It's a pretty long thing. It's worth going through at least once in your life, but we're not going to write it out here. And that now means that our concentration is a function of r, the radius, or the distance from the radial center of the sphere, and time. So for this first problem, these are our boundary conditions. So if you're taking a second derivative in a differential equation, that means you need two boundary conditions in order to satisfy the problem. Our first boundary condition is that the concentration where little r is equal to big R on the exterior is equal to C for all time. The second is that for all time, the derivative of C with respect to R at R equals 0 is equal to 0. And this CS, that is a constant, so we're calling our exterior CS. Now, if you have a time derivative in your partial differential equation, that means that you need an initial condition. And our initial condition is that at t equals 0, C as a function of R is equal to some FR, just some function. And we can set that to 0 or whatever, but I want to set this up in the most generic fashion possible, and that means that we want to write it out this way. Okay, so we've got our differential equation. We have two boundary conditions and one initial condition. But we want to solve this in the most generic way possible, so we're going to transform from coordinates that have units to a non-dimensional variable. And the way we do that is we scale all of our variables. So for example, we're going to have this rho, which is non-dimensional distance. So rho is equal to r divided by big R. So what that means is that the position on the exterior of the sphere is 1, and in the center is 0. So you can see we're basically scaling this so it goes from 0 to 1. Non-dimensional time is tau, which is the d, the diffusion coefficient, times time divided by r squared. And the units work out to be non-dimensional. This is our concentration, chi. Chi is a function of rho and tau, because C was a function of R and T. And it's got to be equal to this. The concentration as a function of position and time minus the concentration in the very center at time 0, divided by the concentration on the surface at time t equals 0, which we know is just constant, minus the concentration in the 0. And for this problem, we can just let this be 0. The truth of the matter is we want to look at the steady state solution. We're not interested in the transient solution. So we're setting it up with time, but we're eventually going to get rid of that. So we're going to set this to 0, which means that now rho chi is equal to the concentration as a function of R and T divided by the concentration on the surface. So the next we have the Michaelis-Menten parameters. So we're going to use nu is going to be Vm times R squared over d Cs, and K, or kappa, we're going to call this kappa, is equal to Km 1 over Cs. And you can see where this comes from here. So we had this expression, right? Well, if you look at this, this has units of mole per meter cubed second. This has units of meter squared per second for d, and then this has units of 1 over meter squared. This has units of mole per meter cubed, which means this first term has units of mole per meter cubed second, so those agree. And that means this also has to have units of mole per meter cubed second. Well, if you look at this, Vm, let's not talk about that, C is mole per meter squared, or meter cubed, Km is mole per meter cubed, C is mole per meter cubed. When you add terms together, when those terms that you add together have to have the same units. So that's how we know this has to be mole per meter cubed, because it has to have the same units as the concentration. And then in order for us to turn this entire unit into mole per meter cubed second, that means that Vm must be mole per meter cubed second here. Because now when we write it out, we get mole per meter cubed second, mole per meter cubed, mole per meter cubed. These cancel out, which gives us mole per meter cubed second, which is why Vm has units of mole per meter cubed second, and that's why Vm is going to be multiplied by these parameters to become a non-dimensional nu, and this is going to be divided by Cs to give us a non-dimensional kappa. So the next step here is to figure out how to take these new variables and apply them. Well, so we have to do a substitution. So for one thing, we have a term in our first equation, our original equation, which is dc by dt. Well, that's d by dt c. Well, d by dt, using chain rule from first semester calculus, we know that d by dt is the same as d by d tau dt. And we know from our definition of tau here that d by dt of dt r squared is just going to give us d rho, and the d and the r squared come out in front, which means that d by dt is equal to d over r squared d by d tau, which means, and then there's a concentration in front, and that concentration we know from our definition here that the concentration is equal to chi times Cs. So chi times Cs, which means that this term dc by dt is equal to d over r squared Cs d chi d tau. And then we do this for all of our other variables as well. So for example, we have a term here. Where is it at? Let me get our equation out. We have to multiply d through here, and we've got a term which is d 2 over r dc by dr, which is 2 dr dc by dr. Well, we take this r and we put in a row. We have a d by dr cs chi. Okay, that means, and that's from the definition of c, because a c is cs chi, and we still have this d by dr. So the d by dr, well, we know that from chain rule, d by dr can be written d rho dr, and then that means that this d rho dr can be d by dr r over r, which gives us 1 over r d rho, which means that we substitute this into here, and we get 2 dr dc by dr is equal to 2 dcs over r squared 1 over rho d chi d rho. So that's going to be one of the terms that goes into our equation. That's number 17. We also have a term in our equation here that is d, and then the second derivative of c with respect to r. So d, second derivative of c with respect to r, well, that's d dr by dr, which is d dr squared, d squared rho, d rho squared cs. And that's from the fact we know that d by dr is 1 over r d by d rho. Okay, so we got that, which means that d squared c dr squared is equal to d cs r squared d squared chi d rho squared. So that gives us the term. And then going into the Michaelis-Menten term, we have a new, in place of Vm, we have new d cs over r squared, and then for c we have cs rho. For km we have cs kappa, and then for c we have cs chi. So the cs's cancel, and we're left with d cs over r squared nu chi over kappa plus chi. So we take all these, 18, 19, 20, 21, and we substitute into our equation 7. Bump, bump, bump. And these terms, they all divide out. And that means we're left with a partial differential equation, which is d chi by d tau is equal to 2 over rho d chi by d rho plus d squared chi by d rho squared minus nu chi cap plus divided by kappa plus chi. And this is the PDE we want to solve. That's the PDE, but now we also have to transform the boundary condition and the initial condition. So the first boundary condition, c at r of t is cs, well, c becomes cs plus rho, and r becomes 1, and t becomes tau, which means that cs, these two cancel, which gives us chi 1 tau is equal to 1. And then our second term, so that's equation 21, our second term is dc by dr is equal to, well, we've got 1 over r d rho by dc cs chi, which gives us, the cs comes out because it's constant, so cs over r d by d rho chi, and we have that equal to 0 at rho equals 0, because rho goes from 0 to 1 on the inside and outside of the sphere. And then the initial condition, which was c r t equals 0 is equal to f of r, well, that makes this chi rho tau equals 0 is equal to g rho. These two are related to each other, f and g, by the fact that g at r over capital R is equal to 1 over cs f over r. Good news is, in our problem right now, this is going to go away because we're not interested in the transient state. We're only interested in the steady state. So we've got now two boundary conditions and a initial condition, which allows us to solve the problem. Except we can't solve it. And the reason we can't solve it is that our equation right here, it has this term, right? It's got a 1 over rho d chi by d rho. That's nonlinear, right? It's nonlinear, 2 over rho d chi by d rho. So we have to do another coordinate transformation, and the coordinate transformation we're going to use is we're going to transform to a u parameter, or a u variable, which is a function of rho and tau, and that u is equal to rho times chi. And let's go through the steps and see how that works, right? So we have our differential equation, and basically for each of these terms, we have to do a coordinate transformation into u. Well, d chi by d tau is equal to d by d tau u over rho, 1 over rho du d tau. So that's the first term in our partial differential equation. Here, d chi by d rho is equal to d by d rho, and here we have u over rho, right? which we're going to write out as rho to the minus 1. And the reason we're going to do that is because rho and u both depend on rho, right? Because u is a function of rho, which means we have to use chain rule to get this, which means that the derivative of, a times b is equal to the derivative of a times b, well, b times the derivative of a plus a times the derivative of b, right? So the derivative of rho to the minus 1 is minus 1 rho to the minus 2 times u plus rho to the minus 1 du d rho. So this is our solution for d chi by d rho. And it looks messy, but don't worry, it will simplify. And we've got a term which is d chi by d rho. Well, we already have d chi by d rho once, so d squared d rho d squared chi by d rho squared is just d by d rho times d by d rho chi, which we already had that solution. So now we take this and we apply it, to each of these terms, that one and that one. Well, if we do that term and that term, each of these terms have then products in them, so we have to take the chain rule, which means that this is the solution to this, and this is a solution to this. And then we take and we multiply our minus 1 through them, and we get 1, 2, 3, these 4 terms. So you can step through the math on that and verify it for yourself. So we can now take this and this and substitute it in to our equation here, here, and here. And here's what we get. Well, we get this long expression, basically, right? And the Michaelis-Menten term, that just becomes a new u over rho, kappa u over rho. And that's the expression. Good news is, if you start multiplying this out, like this, well look, you get all this cancellation. And as a result, and you should step through that to make sure you believe what I'm saying, but as a result, you wind up with du by d tau is equal to d squared u by d rho squared minus nu u over kappa plus u over rho. And this is the PDE we want to solve. Great. Well, we now have to go back and do the boundary conditions as well. So, the boundary conditions, chi at rho equals 1 is equal to 1 becomes u at rho equals 1 tau divided by rho equals 1 is equal to 1, which means we get u at rho equals 1 tau is equal to 1. And then here we've got the derivative. So the derivative of chi with respect to rho evaluated at rho equals 0 is equal to 0. That was our original boundary condition. Well, when we substitute in d rho rho to the minus 1 u evaluated at rho equals 0, we have to do chain rule. We wind up with these two terms, right? And if you look at that, this gives us rho squared u, and this term, let's see, actually this gives us rho over 2u is equal, and this is equal to this, correct, because they're equal to 0, right? So we can set these equal to each other, right? That's the expression. So this is now our boundary condition. And our boundary condition here, if you take this rho to the minus 2 and bring it to the other side, that gives us u is equal to rho du d rho evaluated at rho equals 0, which means that is 0. And if that's 0, then that means that u at rho equals 0 is equal to 0. So you should go through that and feel comfortable with it. But basically, we now have this boundary condition and this boundary condition. And then going to the initial condition, we have this. U rho tau equals 0 is equal to rho chi rho tau equals 0. And that's our initial condition. Great. So, what we have now is we have a non-homogeneous, non-linear mass consumption term that makes this analytical solution, well, impossible if we want to work with the transient state. So in this problem, we're going to start from this point with our PDE boundary condition and initial condition, and we're going to say, okay, we're only going to work with the steady state condition, right? So the steady state condition is simply that dc dt is equal to 0. And we know that dc by dt is equal to dcs over r squared d chi by d tau, which is equal to dcs over r squared 1 over rho du by d tau is equal to 0, which means that this du by d tau is equal to 0, which transforms this PDE and problem setup into a ordinary differential equation now, because u of rho and tau just becomes u of rho, and we got rid of the du d tau saying equal to 0. So we now have this ordinary differential equation, which is the second derivative of u with respect to rho minus nu u over k plus u over rho, and we have the boundary conditions that u at rho equals 1 is equal to 1 and u at rho equals 0 is equal to 0. And this problem is the first problem we want to solve, which you may solve numerically or you may solve analytically. I know it can be solved using a finite element, and I know it can be solved using finite difference. And both those are certainly good solution methods. So let's work on that, and I will start working on setting up the second problem, and then the results from this are going to go into the process of solving the second problem.